Let us review what we did so far. So starting from a scan with many points, we took the approach to identify a certain subset of points, namely those close to large jumps in the range values, and from that computed positions of cylinders, assuming that those combinations of a falling and a rising edge belong to cylinders in the real world. By doing so, we assigned a meaning to those points. So whereas those points here are just XY coordinates, those points are basically objects, and then later we assigned those cylinders to a map, which we made by hand before starting our experiment. And using that assignment, we updated or corrected the position of our robot. Because we used the cylinders, those features, and not the original raw measurement data, this is also called a feature-based approach. And this is called a feature-based map. So now the good thing with that approach is that instead of having to deal with 660 measurements which don't carry any meaning, we can now deal with a subset of, in that case, only 5 meaningful objects. So this makes the method efficient. And also, since these are meaningful objects, assigning them is a relatively reliable operation. But there's a drawback, and we encountered that already. So later on, when we drive along our trajectory, we will only have one single cylinder in our scan, and so our assignment strategy doesn't work. Whereas if we look here, there is still many points. They don't have a meaning, but we probably could match them somehow to a wall. And so the major drawback is, by concentrating on features or high-level objects, which are relatively rare in the scene, we have less work to do in assigning those objects, and the assignment is relatively reliable, but since they are so rare, occasionally there may be no objects in the scene at all, like in this case, and then even though we are having lots of measurements, we may get lost. Now let's think about this wall idea once more. So assume that when we have built this robot arena, we have made a CAD model, so we know the dimensions, and we have put a wall around the entire arena to comply with modern university safety regulations. So think about our robot is here, and it scans all those values with its LiDAR, and maybe here there's a detected pole, and here there's the reference pole. So our approach so far was, we obtained the correspondence. By using this correspondence, we estimate the transformation which is needed to align all the cylinders. And in this case, there's only one cylinder, so that doesn't work. Now think about the wall. Now these measurements here, they're actually lying on the wall. But I don't know where, because these are just points and not features. They don't have a meaning, and I don't know their corresponding partners on the wall. But now let's just do the following. If I just find the closest point on the wall, and then I say this is a corresponding pair of points, exactly as this was a corresponding pair of points, then this correspondence would drag my robot in that direction. As we see here, the correct correspondences would be rather something like that, because from that point we see that we would have to shift the entire measurement in that direction. So, but now if I have lots of correspondences in that way, and also lots of correspondences in that way, then my hope is that all those will in sum tear the robot towards here, whereas those will tear it towards here. So in sum, I hope to get the correct transformation. And as in the previous approach, we will have 2 steps. First of all, find the correspondences, and then estimate the transform. So note that after we have set up such a pair of points, this approach is not fundamentally different from our previous feature-based approach of setting up a pair of cylinders. So now how do we find the correspondences? So in general, this is not an easy problem, because if my LiDAR tells me that it hit an object here, then I would have to scan my scene for objects which may have been hit by the LiDAR and then assign the closest object. But in our case, things are much simpler, because our arena consists of 4 axis parallel line segments. In the left, the right, and the top and the bottom, whenever there is a ray hitting a point xy, we can do the following. Because the left wall of our arena is at x equals 0, we may just test if this x is smaller than a given threshold, meaning this point is inside this band. And if this is the case, we define this point being the corresponding point. And this is very easy because this point has coordinates 0 and y. And the same holds here. If x minus right smaller than the threshold, the right is this value here, then this partner will be right and y. And so we will get all the pairs for the estimation of our transformation. Now instead of using every single beam, we will do a subsampling. So we will only look at every nth beam so that our matching algorithm is faster. So I want you to implement this, and the offline version is SLAM5a find wall pairs. So the only function you'll have to implement is this get corresponding points on wall. So this function receives a list of points, and it has the dimensions of the arena as default parameters. And you can see here the arena is exactly 2 times 2 meters. And there's this distance threshold being 150 millimeters or 15 centimeters. Now the task of this routine is, for every point in points, check if it is within this band of the left wall, the right wall, the bottom wall, or the top wall, and if so, add the point itself to the left list and its partner on the wall, meaning the point with the modified coordinates, to the right list, and then return both lists. So in my implementation, I checked for the left and right, bottom and top wall in that order, and when I had a match for the left wall, I didn't care about possible other matches. Now let's have a look at the rest of the program. So I told you we will use a subsampling of the scan, and this is done here. That's already implemented. Then let's have a look at main. Well, main function is pretty short. Now we don't have those thresholds for cylinder detection anymore. Here we have our filtering loop. We compute the pose as usual. Then we get the subsampled points of the current scan and convert those to world coordinates. Then we're using this matching routine you'll have to write to get left and right pairs. And in the end, we output a list which contains both the left and right list. So what we write out is, for every point that has a closest match on a wall, we write out the point and the match. Now before you start, let's have a look at how the results will look like. So your code will produce a find wall pairs text, and if you open this, you will see the following. Here's the robot in its start position, and at that position, looking down there, it will scan almost the entire arena. So we won't use all the scan points, but we have this subsampling. So what you see here is a set of subsampled points from the current scan. What you see down here is the corresponding points which are on the bottom wall. And similarly, you see here the corresponding points on the left wall. So as we go through the scene, you see as we start to turn, there's still correspondences here, but our distance threshold will omit point pairs which have a larger distance than 15 centimeters. You can see this nicely here. So of all those points, only those correspondences remain. So now please implement this.